I'm going to factor 11 expressions, where each one gets more difficult than the previous one. Let me know in the comments how far you could get, and which ones you found difficult. Level 1. I have an expression made up of two terms that can be common factored. If I look at the coefficients, I see 12 divides evenly into both 24 and 36, so I'll common factor out a 12. And then if I look at the variable part of each term, I notice they both have factors of x. I'll take out the one with the smaller exponent. And then to get the second factor in my expression, I now have to divide both of these terms by my common factor. So I'll leave my factor of 12x squared out front, and then I'll simplify my second factor by doing the divisions. I need to do 24x squared divided by 12x squared, which is 2. And I have to do 36x to the 5 divided by 12x squared, which is 3x cubed. And there we have it. Level 1 has been factored. Level 2. I have a quadratic trinomial where the a value, the leading coefficient, is 1. To factor this, I can use a sum and product factoring method, where I find a pair of numbers that have a product of the c value, negative 28, and a sum of the b value, which is 3. The numbers that satisfy that product and sum are 7 and negative 4. 7 times negative 4 is negative 28, and 7 plus negative 4 is 3. So I know I can rewrite that quadratic in factored form, right? A product of two binomials, where the first term in each binomial is an x, and the second term in each binomial, I just add each of these numbers that satisfy my product and sum. So my factors are x plus 7 and x minus 4. Here we go. Level 2 has been factored. Level 3. Once again, I have a quadratic trinomial. I see I can actually start by common factoring out a 2 from all three terms. So I'll remove a factor of 2, and then divide all three terms by 2, which would give me 2x squared plus 3x minus 20. And now for the rest of this question, that first factor of 2 is just going to stay at the front, and I'm going to focus on this quadratic that's in brackets. This time I have a quadratic whose a value is not 1, it's 2. So I'll have to use a sum and product method called decomposition. I want to find numbers that have a product of a times c. So 2 times negative 20 is negative 40. So I need a pair of numbers that multiply to negative 40. But that pair of numbers also has to add up to the b value of 3. The numbers that satisfy that product and sum are 8 and negative 5. What I have to do with those two numbers is split this middle term, this 3x. I need to split it into 8x minus 5x. I'll leave the rest of the expression exactly as it was. And now I'll factor by grouping. I'll consider the first two terms in brackets its own group, and the last two terms in brackets a group. When I remove a common factor from the first group, I notice that I could take out a factor of 2x. I need to then divide both of those terms by the 2x I'm taking out, which gives me x plus 4. And now I need to look at the second group. I could common factor out a negative 5, and then divide each of those terms by negative 5, leaving me with a factor of x plus 4. Notice inside the square brackets, I have two terms. And you notice what's in common between those two terms is the x plus 4. So I could common factor out an x plus 4 from both of those terms. When I divide both of these terms by the x plus 4 I'm taking out, both of those x plus 4s cancel, and I'm left with 2x minus 5 as my last factor. And there you have it. Level 3 has been factored. Level 4. I have a trinomial where the factoring method of decomposition that we did in level 3 will work again. I need to find numbers that have a product of 2 times 27, so a product of 54, and a sum of negative 21. The numbers that satisfy that product and sum are negative 18 and negative 3. So I'll split the middle term into negative 18 x squared y minus 3 x squared y. And then I'll leave the rest of the expression as it was. And now I'll factor by grouping, where I consider the first two terms a group and the last two terms a group. From the first two terms, I could common factor out a 2x squared. When I divide both of these terms by 2x squared, I get x squared minus 9y. And now from the second group, I can common factor out a negative 3y. And then when I divide them both by negative 3y, I get x squared minus 9y. Once again, notice with these two terms, I have the common binomial of x squared minus 9y. So I can common factor out that x squared minus 9y, and when I divide both of these terms by x squared minus 9y, the x squared minus 9y parts of those terms cancel, and I'm left with 2x squared minus 3y. And there we have it. Level 4 has been factored. Level 5. The first thing I notice is that all four terms have a factor of x. So I'm going to common factor out an x from all of the terms. I'll put the x out front, and then divide all of the terms by x. Inside the brackets, I have four terms. Let me try factoring by grouping. The first two terms in brackets are a group. The last two terms in brackets are a group. From the first group, I could remove a common factor of x squared, y squared. When I divide both of these terms by x squared, y squared, I get x minus 3. From the second group, I could common factor out a negative 9z to the 4. And then when I divide both of these terms by the negative 9z to the 4, I get x minus 3. Because this is a common binomial, I can remove that as a factor. And when I divide both of these terms by the x minus 3, the x minus 3's cancel, and I get x squared y squared minus 9z to the 4. I can actually factor this further. Hopefully you notice that what I have here is a difference of squares. Let me rewrite it so you can see that more clearly. The x squared y squared, I could rewrite it as an xy, all being squared, minus the 9z to the 4, I could rewrite that as a 3z squared, all being squared. And now I can follow the rule for difference of squares. My difference of square rule tells me I take both terms that are being squared and create my two factors. My two factors would be xy minus 3z squared times xy plus 3z squared. And there we have it. Level 5 has been factored. Level 6. Once again, I have a trinomial, and I can rewrite this in a quadratic form so you can see that we can use a sum and product factoring method. I'm going to rewrite that x to the 6 as an x cubed squared. And then to make it very obvious what method we'll use, I'm going to say let k equal x cubed. So that would mean my expression could be written as k squared minus 26k minus 27. Now that's a quadratic where the a value is 1. So I just need to find numbers that have a product of c, negative 27, and a sum of b, negative 26. The numbers that satisfy that product and sum are negative 27 and 1. So I know that this quadratic would factor to k minus 27 multiplied by k plus 1. But remember, those k's are actually x cubed. So let me change them back to x cubed. And while I do that, I'm actually going to change the 27 and the 1 to be written in terms of a perfect cube number. 27 is a 3 cubed, and 1, I can think of that as 1 cubed. Hopefully you now see that we have a difference of cubes and a sum of cubes. So I could follow the difference and sum of cubes formulas. Let's look at the difference of cubes first, and let me use the difference of cubes formula to factor that. That formula would tell me that this is equal to x minus 3 multiplied by x squared plus 3x plus 3 squared, which is 9. And now let's look at this sum of cubes, and I'll follow the sum of cubes formula. The sum of cubes formula tells me that would be equal to x plus 1 times x squared minus 1x plus 1 squared, which is 1. And there you have it. Level 6 has been factored. Level 7. This time I have an expression with 6 terms. Anytime there's an even number of terms, maybe grouping will work. So I'll think of the first 3 terms as a group, and the last 3 terms as a group. From the first group, I can take a common factor of x cubed, and when I divide all 3 of these terms by x cubed, I get 3x squared plus x minus 4. From the second group, I can common factor out a negative 8, and then when I divide all 3 of these terms by negative 8, I get 3x squared plus x minus 4. Notice with both of these terms, I have the common binomial of 3x squared plus x minus 4. So I can common factor out the 3x squared plus x minus 4. And when I divide that out from both terms, I'm left with x cubed minus 8. But instead of writing 8, I'm going to change it to a 2 cubed so you can see that we have a difference of cubes. Now I'm left with a quadratic that I could factor further, and a difference of cubes that I could factor further. Let me start with the quadratic. The a value is not 1, so I'll have to factor this by decomposition. I need to find numbers that have a product of a times c, so a product of 3 times negative 4, which is negative 12, and a sum of the b value, which is 1. The numbers that satisfy that product and sum are 4 and negative 3, so I have to split the middle term into 4x minus 3x. I'll leave the rest of the expression as it was, and then I'll continue by factoring this by grouping. I'll take a common factor from the first two terms. I could take out an x. The last two terms, I could take out a common factor of negative 1. I have a common binomial of 3x plus 4 that I could factor out. When I divide both terms by 3x plus 4, those are gone, and I'm left with x minus 1. Okay, that's just half of what I wanted to do. I've now factored this part of my expression. I also need to include this factor that is a difference of cubes. If I follow my difference of cubes formula, I know this would be equal to x minus 2 times x squared plus 2 times x plus 2 squared, which is 4. So let me continue writing that all the way down just to make my answer complete. And here we have it. Level 7 has been fully factored. Level 8. I have a degree 4 polynomial expression where I think the only way to start factoring this would be for testing for zeros. I wouldn't test just any number though. I would test factors of the constant divided by factors of the leading coefficient. That's the rational zero theorem. Factors of 12 are plus or minus 1, 2, 3, 4, 6, or 12. And factors of 3 are plus or minus 1 or 3. So if there's a rational number that makes this polynomial be 0, it would be one of these numbers divided by one of these numbers. Let me do a quick test. I'll call this function f at x. If I subbed negative 1 into that function for x, it would make it be equal to 0. So that tells me that x plus 1 is a factor. So I know this expression can be factored to x plus 1 times whatever the quotient is when I divide this by x plus 1. And I can do that division using a method called synthetic division. I'll set up a synthetic division table off to the side. The 0 of the divisor would be negative 1, so I write that here. And then I just take the coefficients of each of my terms and write them up here. And then the synthetic division algorithm tells me to bring the first term down. I then find the product of negative 1 and 3, which is negative 3. And I then find the sum of that column. 2 plus negative 3 is negative 1. And then I just repeat that process. And right here, I see what the quotient is. 3x cubed minus x squared minus 20x minus 12. And now I need to focus on, can I factor this cubic any further? If I test for zeros again, by testing factors of negative 12 over factors of 3, I would see that negative 2 makes this be 0. So I know I could factor that cubic into x plus 2 times whatever quotient I get when I divide this cubic by x plus 2. I'll do that division off to the side as well. The 0 of the divisor is negative 2, and then the coefficients of that polynomial are 3, negative 1, negative 20, and negative 12. And then I'll quickly run the synthetic division algorithm. And I see that my quotient is 3x squared minus 7x minus 6. Now I'm just going to make some room to continue my work. I just need to finish by factoring this quadratic. The a value is not 1, so I'll need to find numbers that have a product of a times c, a product of negative 18, and a sum of the b value, negative 7. The numbers that work are negative 9 and 2. So I have to split this middle term into negative 9x plus 2x. And then I'll factor the quadratic by grouping. First two terms are a group, last two terms are a group. From the first two terms, I can common factor a 3x, and from the last two terms, I can common factor a 2, which leaves me with x minus 3 again. So I can common factor out that x minus 3, which then leaves me with 3x plus 2 as my last factor. And there you have it, level 8 has been factored. Level 9. The first thing I'm going to do with this question is from these last three terms, I'm going to common factor out a -1, and you'll see why in a second. Now you should notice that these first three terms are a perfect square trinomial, and these last three terms are a perfect square trinomial. So when I factor them both, I'm going to get a binomial squared for each of them, which will leave me with a difference of two perfect squares. Let me make sure you see both perfect square trinomials. This first one, the first term is a perfect square. It's a 2x being squared. The last term is a 3y being squared. And the middle term is double the product of those perfect squares, which means it would factor to 2x plus 3y all squared. Now let's focus on the second perfect square trinomial. The first term is a perfect square. It's a 3m being squared. The last term is a 4n being squared. And the middle term is double the product of the 3m and the 4n. So for that reason, I know that it factors to 3m plus 4n squared. So now I have a difference of squares. So if I follow my difference of squares formula, I get 2x plus 3y plus 3m plus 4n multiplied by 2x plus 3y minus 3m plus 4n. I should simplify this second factor by subtracting both of those terms. And there you have it. Level 9 has been factored. Level 10. With this polynomial, we actually have a difference of cubes. It's pretty easy to see that this last term is a perfect cubed value. It's just a 4y being cubed. But it's a lot more difficult to see that this is a perfect cube value. That's actually a binomial cubed. Let me write the formula to remind you about that. An a plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. So if I look at these four terms, I'm going to rewrite them in a way that you can see that it follows the binomial cubed formula. First term is a 2x that's being cubed. The last term is a 3 being cubed. So this 2x and this 3 are like the a and the b of this formula. This term is supposed to follow this pattern. So let's see, is it equal to 3 times the a value squared times the b value? If I were to simplify this, I would have 36x squared. Great. Now does this term follow this rule? Is it equal to 3 times a times b squared? If I were to simplify this, I would get 54x. So because it follows this structure, I can factor it to a plus b cubed. So I can just factor it to 2x plus 3 cubed. And let's not forget about this term. I'm subtracting 64y cubed. I could rewrite that as a 4y all being cubed. So now I can follow my difference of cubes formula. My difference of cubes formula tells me to write this as 2x plus 3 minus 4y multiplied by 2x plus 3 squared plus 4y times 2x plus 3 plus 4y squared. All I have left to do now is to simplify inside of that factor. 2x plus 3 all squared will be equal to 4x squared plus 12x plus 9. I'll distribute the 4y to both of those terms, giving me 8xy plus 12y. And 4y all squared is 16y squared. And then inside that factor, there's nothing to simplify, so I'll leave it. Level 10 has been fully factored. Level 11. For this trinomial, you might try a sum and product factoring method, but nothing multiplies to 16 and adds to 4. But what you should notice is that this expression is awfully close to being a perfect square trinomial. The first term is a perfect square, and the last term is a perfect square. Let me just make a note at the top that the first term is an x squared squared, and the last term is a 4 squared. In order for it to be a perfect square trinomial, in the middle would have to be double the product of both of those perfect square values, x squared and 4. So it would have to be 2 times x squared times 4. This is 8x squared, but in our trinomial, the middle term is just a 4x squared. If it was an 8x squared, I'd be able to factor it. How can I make this an 8x squared without changing the value of this expression. What I'm going to do is I'm going to add and subtract 4x squared to it. Let me show you what that looks like. Of x to the 4 plus 4x squared plus another 4x squared plus 16, right? That makes the middle term be 8x squared now, which is what we wanted. But I've changed its value, so I have to also subtract 4x squared, and I'll do that off at the end. But notice, what did I create? I have a perfect square trinomial right here, so that'll factor to a binomial squared. And this is also a perfect square value. It's a 2x being squared, so I now have a difference of squares. Let me do the factoring so you can see that. These first 4 terms, let me rewrite them in a way that you can see it's a perfect square trinomial. The first term is an x squared squared. The last term of it is a 4 squared. And the middle term, 8x squared, is equal to double the product of x squared and 4. So I know that would factor to x squared plus 4 all squared. And now when I look at this expression, I'm going to rewrite that as a perfect square as writing it as a 2x all squared. So now I have a difference of squares. So I'll follow my difference of squares formula, which would tell me that this is equal to x squared plus 4 plus 2x multiplied by x squared plus 4 minus 2x. And let me just change the order of the terms in each of those factors. And there you have it. Level 11 has been factored. Hopefully you were able to do well and also maybe learned a little bit about factoring. Make sure to leave a comment about what topic you want to see a series about next. Jensen Math!